Welcome to the video on the Superstructure shed by William Gower, Edward Smart and Frederick Moore. The wind load determination was a relatively simple but highly important task. The wind loads that would be determined here would influence the design of all the members within our structure. Using tables from AS 4055, we were able to determine the wind class, the wind speed, wind pressure and the pressure coefficients for our structure, which you can see on your screen there.
Purlin design. For the purlin design, the first thing that we were to consider were the dead loads that would be acting upon this purlin. These were the roof cladding, the insulation and the self-weight of the purlin. We then obtained the live load that was necessary from AS 1170.1 and then we found our wind pressure from our given wind region, terrain category, topographic class and shielding class, which we then found our wind class to be N4. With these three loads now calculated, we were able to start designing our purlin. At first we designed our purlin for downward pressure from these three loads, which gave us a Z150-15, but we quickly realised that because this purlin was able to withstand the pressures coming down, it may not necessarily be able to withstand the pressure of outward force from the wind. This led us to having to choose a larger cross-section of Z purlin to be able to withstand both of the pressures, upward and downward. Serviceability was the next step, in which we found again we had to increase our member size twice to be able to withstand the requirements. From our first selection of our purlin compared to the last selection of our purlin, it considerably increased in size. It was then discussed whether it would be more beneficial of decreasing the spacing to therefore keep a smaller member, which may have been a more cost-effective idea.
Rather than use the SpaceGas software, the three of us decided to use the skills we learnt last year in Structures 1 to determine the wind bracing. After determining the wind forces in the middle and ends of the frame, we were able to draw free body diagrams and use our skills from Structures 1 to determine the forces in each member of the wind bracing. Due to symmetry within the design, we would only have to determine the force of a few different members. Once the forces were determined, we were then able to design the tension and compression members using the design section tables.
Rafter design. For the rafter design, we already had all the other loads from the previous purlin example, so we only had to consider the rafter weight at 0.1 kilonewtons per metre squared. We also had to consider for the central rafter a 500 kilogram capacity for the ability to lift an engine. We decided to consider this engine as a UDL. Then the same process was undertaken by using the load combinations to find the most critical for downward pressure and upward pressure, suction. For the rafter design, it was the top flange and bottom flange when under compression is how the design was obtained. When both of these met the requirements, it was then again serviceability that was done from Australian Standards 1170.0 for the maximum deflection allowed, which did take a few goes to reach a suitable member, as our chosen member sizes were quite insufficient to begin with, so it took 2 or 3 tries to find a member that had the capacity to withstand the deflection amount. For the rafters on the end, the same process was taken, except there was no 500 kilogram UDL, and we assumed that both rafters on each end would be under the same loads.
Column history. Columns date back to as early as 2600 BC. We use our dead load from part 1. Our Gmax is 2.37 kilonewtons and our Gmin is 1.92. We also use our live load from part 1, our live load being 6.14 kilonewton meters. We also use our wind load from part 1, our pressure being 21.9 kilonewton meters, and our suction being negative 36.2 kilonewton meters. We then get our load combinations, adding everything else, adding all of them together. We then get our most severe loads. Our most severe is 24.7 for compression and 34.5 for our tension. We then get our buckling about y-axis, but first we've got to do our interpolation. So we then get, for an example, y1 plus bracket x minus x1 times y2 minus y1 bracket divided by x2, take x1 equals 183 plus bracket 3.8 take 3 bracket times 111 take 133 divided by bracket 4 take 3. This gives us a total of 125.4. We then go to our tables and we work out our suitable member is 100 UC 14.8 125.4. We then do our buckling about x-axis. First, our common column width is 100 mil. Our load efficiency equals 50 mil, divide that by 1000 is 0.5 m. Our m equals 24.7 times 0.05 equals 1.24 kilonewton meters. Again, interpolation. Then after working that out, you get the suitable member, which equals 100 UC 278.5 kilonewton meters. We then get our combination of compression and bending moments. You then have to make sure that the total figure is less than 1. In this case, our column is suitable because after doing 24.7 divided by 12.5 plus 1.24 divided by 278.5 equals 0.20. So this means our column is suitable. Tension for the columns. Tension from table 7.1, 100 UC 14.8 welded no holes equals 543 kilonewton meters, which is greater than 34.5. This means column 100 UC 14.8 is compatible. Discussing about the design capability table, the member selected 100 UC 14.8 is the most economical and efficient member available for use. It is engineered to take the required load and more, as you can see from the combination of compression and bending moment. As you can see from above, the total of the combination of compression and bending moment equals the total is less than 1, as the member chosen was the lowest available member. If the tables had a more lower member, a more economical member could have been chosen. Compare and discuss the maximum load and the size of the end and intermediate columns. The end column compared to the center column has a smaller attributed area. This leads to a smaller dead load to carry a smaller load combination. The end column would be smaller than the center columns. If the table showed a smaller columns, they could then be used, which would make the design more economical. However, corner columns do not have to have such a small diameter compared to center columns due to the